So it is my pleasure to welcome you to this talk. This work is led by NYU AD, NYU, the Joint Center for Cybersecurity, and also in collaboration with other institutions as listed here. So what we are looking here at are security implications for the hardware, that is, for the design of integrated circuits. And I will talk today about what is security closure physical layouts, why do we need this? Then I will talk about how do we achieve this, and I will walk you through some case studies there. And later on we will also look into some challenges and strategies promising for future work in this context. And given that we are looking at the hardware of integrated circuits, this talk might be a bit technical every now and then, but I'll try my best to keep it on the high level and on the main messages here. Before jumping into the topic, let's take first a look at the IC supply chain and the range of threats we are facing here. So what you'll see here is an outline of the different stages in the life cycle or the supply chain of ICs. And also highlighted here are different types of attacks: design attack, hardware attack, logistics attacks. And nowadays, given the fact that large parts of the supply chains are outsourced, we do indeed see this variety of threats affecting directly the hardware, or even then the data in the field, which is run on the hardware. So let me be a bit more specific. What are the actual threats we are looking at here in this work? Now, illustrated on the upper left is a measurement for the voltage, and we see those fluctuations, which are also called IR drop. And this IR drop is caused basically by the switching activities of a circuit when some computation is performed. And such observations can be made by an adversary in the field, and they can also be well correlated with sensitive computation, let's say some cipher operation, and accordingly sensitive data like a secret key for cipher operations can be inferred. These kind of attacks are called side channel attacks, and this particular one is then called a power side channel attack, which is quite advanced and quite helpful for an adversary to infer secret data. In the upper right, we are looking at malicious hardware modifications, which are also called Trojans. And in this case, we are looking at the so-called A2 Trojan. What you'll see highlighted here in this zoom in is that this A2 Trojan basically requires just a few additional gates, that is a few additional components or devices in the circuit to be inserted, and also a little additional routing. So such a small Trojan is considered not difficult to realize by adversaries in either the mask or the manufacturing facilities, so this is indeed a threat to be concerned about. Moving on to the lower left corner, what we see here is a top view and a cartoon representation for what is called electro-optical probing. So this is basically a failure analysis technique which helps us or an adversary to infer the charges in the logic as well as in the memory cells. And with this approach, we can basically understand the bit 0 or 1 as in literally reading out the data at runtime on the hardware. And this is quite powerful as well, as you can imagine. On the lower right, what we see is a cartoon illustration for fault injection, indicated here as in terms of optical means, so laser light. This is what this cartoon should represent. And the key idea is that by inducing some physical faults, in this example again laser light, the behavior of the circuit can be thrown off, leading to some failures or glitches in the hardware, and in turn of corruption of some data. Now these kind of attacks are often combined with sampling and analytical attacks later on to also infer then the secret keys or any other secret data of interest. So with this background, let us now jump into the topic, security closure. What is this and why do we need this? So if you want a one-line summary, I would say security closure means to enable CAD tools to harden layouts against layer level threats. And CAD tools being the software tools which are used nowadays to help design integrated circuits. Why do we need this? Well, we've just seen that there are different threats which exploit vulnerabilities directly at the layout level. So that is one key reason. Another is that going forward, we can expect even the design process itself to be more and more outsourced. And accordingly, we would want to have independent verification and validation and hardening of layouts as needed. And another reason is actually that also we want to maintain security efforts which had been maybe introduced earlier in the design process. As in that we really want to have a closer stage here, in terms of security. So to make this point a bit more clear, let us look at an counterexample. We just talked about fault injection, and illustrated here is such a proposed scheme for detecting a laser fault injection. So there is some additional circuitry which would basically detect the moment there is some laser fault injected on an AES, that is a crypto or cipher module, and it would be accordingly shut down to protect the data. So far so good. However, there might be also other security vulnerabilities arising from such a scheme. And indeed, what the follow-up work has observed is an unstable behavior of this alarm signal, which is used to shut down the circuit, when the attacker on purpose is reducing the strength of the laser light. So what we see here on the right as a plot is basically the number of traces needed to infer the secret key. So the more traces needed, the more resilient is the scheme, or the more secure it is. And highlighted in red is basically when the laser was of strong light, so this was all clear, there was no security vulnerability. But however, as indicated, if the laser strength was reduced on purpose, the alarm signal was unstable and the secret key could be successfully inferred with way less traces here. So that means what we see in here is that a new side channel is arising, and this is a clear motivation that we need to have a holistic approach for security closure, also taking into account the physical realities of the hardware. So moving on, the question is now, how can we achieve security closure? What we are looking at here now is an overview on a regular commercial CAD flow, illustrated here in the middle. We do have different stages in such a CAD flow or chip design flow, going from the system description through a behavioral model down to the gate level. That means a representation of the circuit of individual cells or gates, like a Boolean AND function, and then eventually through the physical design to the real physical layout. And what we see now here is that security closure is connected here with the physical design, but it doesn't mean that other stages are not relevant for security, as we already indicated earlier on. And we will be extending this view on a CAD flow, on a secure CAD flow anyway later on. So this is basically an overview of what we are looking at, how to achieve this. So also here, let me be a bit more specific by walking you through some case studies. The first one is closure against Trojans, that is the malicious circuit modifications. We did implement this in a commercial CAD tool, but this is basically generic, so the principles we followed are generic. This is really just a case study we followed. And a key point here to take away is that this is fully integrated as well as automated with visual feedback as well for the designer. So how does this feedback look like? What we are looking at here is top view on the placement of the cells and a layout of an AES cipher. We do have highlighted in blue the sensitive assets that are the key registers holding the secret key. And we do see highlighted in red as well as in yellow vulnerable placement sites, which are either fully or at least partially vulnerable, as in routing resources to connect cells may or may not be available. So this kind of visualization is important, but also the underlying assessment in terms of metrics is quite important as well, to accordingly guide also the chip design tools or the CAD tools. So what can we do now in terms of mitigation after we are able to assess the threat of Trojan insertion? Well, looking at a little more detail, what we see here is a zoom in on the layout with different utilization numbers. That means basically density of the placement and routing. And what we'll see to the left is that with a more relaxed utilization or placement, there are more vulnerable sites available, highlighted in red here, versus the example here, we do see less of such vulnerable resources. So that means Trojan insertion by some adversaries is simply more difficult to achieve. At the same time, however, we've seen that this layout here on the right with 80% utilization is more difficult in terms of time enclosure. That means to make sure that the circuit will really work as intended. And it will also have an additional cost on the power, performance, and area of the circuit envy. So that means there's an underlying trade-off for the regular objectives for chip design as well as security. And this has to be addressed like we did in a holistic and streamlined framework. Another case study we looked at is closure against frontside probing. That means probing through the metal layers, as illustrated also here now to the upper right. So this covers actually multiple attack vectors, like electro-optical probing we've seen before, e-beam probing or micro probing is now also illustrated here. And we perform the assessment using a notion of polygon level exposure, literally looking at the polygons of the physical layout. And we also consider angle attack vectors using simple trigonometry and also projections. So just looking at a few simple examples, what illustrated is here now are different cells or gates with different exposures. So this one is largely exposed. And the counterexample here, this one in the middle, is much less exposed. Now, naturally, what degree of exposure is still considered to be vulnerable, that depends entirely on the technology capabilities of the attacker as well. What can we do in terms of mitigation? So we can actually shield the upper metal layers as illustrated here. So there is some additional shielding introduced in higher metal layers. So what we are looking here at is a top view again of the routing of the metal layers with different colors representing different parts of the stack or different layers of the metal stack. And illustrated now here is also the placement of the sensitive module, which is basically hidden beneath this shield in the higher layers. So, and here on the right, we do see a zoom in on those dedicated metal structures which are shielding now from the top against such front-side probing attacks. Another mitigation technique could be to also reroute sensitive nets in lower layers or widen other non-sensitive nets and so on. So the defense schemes are basically what we're looking at here based on routing. So let us shift gears a little bit now. By looking into challenges and promising strategies, so we do have a few things here to consider, which are basically interesting for those who want to also jump into this research direction and tackle new things. So first, security closure is limited in principle since we are looking at the layout level and we are looking at this in terms of a sign-off stage. That means, for example, architectural vulnerabilities cannot be fixed so late in the design process. And to handle this better, what we think is a interesting strategy is to integrate such closure means also with a secure by design CAD flow, what is outlined now here. So you see here, in addition now, we do have security specification and verification. So specifications as in what are sensitive assets, what are the attacker capabilities and so on. And verification as in we do have a bottom-up assessment of the security or rather the resilience like we've seen with these case studies for different examples already. At the same time, we do want to have a top-down guidance by the commercial tools as best as possible for optimizing both chip design metrics in general and security metrics. Another challenge is the scale and the complexity. Since we are literally looking at billions of polygons in a sophisticated arrangement, we do see an interplay of various physical effects. So this is really quite challenging problem in general. And again here, that means we want to leverage the CAD capabilities as best as possible. We do see potential for scripting early on, like we also did in these case studies, but we also see the need for custom code later on for high performance closure schemes. Next, we see that there's a lack of a holistic approach, as in there are different approaches already established against different kind of threats. But in the end of the day, they all have to work on the same layout fabric, so they should be more streamlined. In this context also, a challenge is the composition of different techniques. There could be higher order vulnerabilities arising. If you just recall this example, what we gave earlier with the detection of laser faults, which gave rise to a new side channel. So that means what we really need here are cross-disciplinary efforts from the security community, the layout experts, as well as the CAD users, to have accordingly holistic approaches. And what is of course also needed is a technology-centric view describing those defense means, but also the threats. And of course we need metrics to guide the design tools. And speaking of metrics, so it's also clear that each threat has its own particular metrics, and they can also behave quite different, like step functions. So if you will an example, there could be the mitigation or the handling of faults. So in a regular flow, it would be good enough to reduce the number of possible exposed faults. Whereas for security, for an attacker, it might be good enough to just trigger one specific fault only. So for security, that means you probably must spend a certain minimum amount of efforts for hardening the layouts. Otherwise your security will be broken. But at the other hand, spending more might also not be beneficial. So this is quite a different behavior in contrast to traditional chip design metrics. And accordingly, what we see here is, again, we need co-optimization of those different techniques along with the layout itself. We need this integration in a secure by design CAD flow. And maybe given those different metrics, those different behaviors of metrics as well, also guidance by machine learning could be quite interesting here. Finally, yet another challenge are advanced nodes, because here we are looking at different, smaller and more complex geometries of the cells. And this goes two ways, as in the attackers would also need advanced capabilities like E-beam probing. So illustrated here as a classical infrared probing, which may not be good enough to read out data at runtime from such advanced geometries and cells, whereas E-beam as illustrated here, or also here in another work, can still be leveraging or helping an attacker to figure out the data at runtime. So this is the one aspect. The other aspect is also that there are even more effects coming into the picture with advanced nodes in particular, namely reliability effects. One prominent reliability effect is called aging. So that means literally that circuits with different mechanisms can also degrade and they can age. And basically the circuit would become slower. And there's also a shift on the power profile. Typically, these aging effects are covered during design time as well, using something like timing outbands or design margins. So that is possible in principle. However, there's an important point to consider is that these aging mechanisms do actually depend on operation conditions. So what we see here is different temperatures for the circuit in operation, different voltages. And what we'll see, the higher the voltages, as well as the higher the temperatures, the faster the aging is. And this in turn has an implication for security. Now we've just seen that basically somebody can control the aging and the related impact. So that means accordingly for security, we would need to consider such effects at the circuit level. And this is also something we looked into, and maybe without going into further details here, the key idea is that we did consider aging effects, with the libraries of the standard cells, of the logic components in there. And this in turn helped us to simulate the resilience against the power side channel over the lifetime. And this is really just an example here illustrated. And we do see that indeed with aging considered and for different voltages, we have a different impact on the security, that is on the resilience of the circuits. So in short, these kind of advanced assessments are required for security. They are available in principle for CAD flows, but they have to be also applied specifically with security in mind. Another interesting reliability effect are migration effects and interconnects. And I'll promise this is the last technical thing we are looking into. So you'll see outlined here on the right that there are basically different effects, and they all have a rather complicated interplay, which requires some physical modeling and physical understanding. But most of the failures of interconnects are due to electromigration, that is literally of movement of the atoms of the materials in the interconnects, in the wires, when the chips are under stress. So these effects, migration effects, they can and have been considered in a conventional design flow by different means. Basically, again, we need physical modeling, and with such modeling, we can then also account for these issues in the design flow. Now, the problem, however, is that malicious exploitation of such effects has been largely overlooked so far. And we think this is indeed a serious threat, as in there could be stealthy zero-gate Trojans which will make the chip potentially fail. And how can this look like? Well, there could be simply an undermining of the migration robust design. So illustrated here are examples where basically at the interconnect level, some of the features for making them actually robust against migration, such as reservoirs here, are by an attacker simply removed, or they are reorganized as in shifted. There could be also some rerouting in terms of how the vias are configured and how currents are flowing in the wires in the interconnects. So this is basically something what we believe is not too difficult at all to achieve for an adversary, but in turn more difficult to defend against. So we see this is probably possible using tight routing defenses, but still this is something highly relevant to look into in future work. So let me conclude now. What we looked into today is that there are indeed many threats exploiting vulnerabilities directly at the layout level. And CAD tools, however, are not focused on security yet, so there is a gap here. We accordingly proposed or outlined the need for security closure, and we also made some suggestions how this could be realized. We also talked about some examples for those manifold complexities and some aspects to consider. So if you recollect, here we looked into the assessment of Trojan insertion. Here there's a defense against probing attacks. Here there was this example about the higher order vulnerability with some new side channel arising. And here this is the outline of advanced electromigration based Trojans or failure attacks on chips. So you'll see here with these different complexities, there are indeed interdisciplinary efforts required, but it is still a possible thing to address. And this is, like I said, current research and state-of-the-art work. We have basically described here the problem. We outlined some case studies, gave an outline on challenges and strategies, and you'll also find more details if you wish on my website, where we have linked to research papers on this very topic. And finally, I'd like to encourage you for a contest at ISPD, the International Symposium on Physical Design. So the contest is on this very topic of security closure of physical layouts. And again, I'd like to invite you to participate in there. With this, thank you very much for your attention and for your interest, and I'm looking forward to some discussion.